Explanation on using differentials to approximate volume changes. We are examining a sphere and asking how its volume changes when its radius grows just a little bit. Here is the sphere, its radius, and an extra tiny piece labeled d are representing the added radius. First, recall the volume formula for a sphere. The volume is 4/3 times pi times r cubed. Taking the derivative with respect to r gives 4 pi r squared, which tells us how fast the volume is growing for a radius r. The differential dv approximates the change in volume. So we multiply 4 pi r squared by the tiny radius increase dr. This means we are basically using the surface area at radius r as an estimate of how much volume a thin layer of thickness dr adds. Let's plug in specific values to see this approximation in action. Suppose the radius is 6 units and it grows by 0.2 units. The actual change is delta v equals 4/3 pi times 6.2 cubed minus 4/3 pi times 6 cubed. The approximation gives dv equals 4 pi times 6 squared times 0.2. Now evaluate both expressions. The actual difference is about 93.47 cubic units. The differential gives about 90.48 cubic units. The error is around 2.99 cubic units, so this approximation is off by a few units. Finally, compute the percentage error. We take the absolute difference between delta v and dv, divide by delta v, and multiply by 100%. That gives approximately 3.2% error. In conclusion, differentials let us use the slope of the volume function, here the surface area, to quickly estimate small changes. The approximation stays very accurate when the